Okay, well, thank you for coming. My name's Stephen. I work for Intel. I've been with Intel for about 15 years now, and I work in the compiler team, so working with the people who make the compilers. And I spend some of my time doing things like this, talking at conferences, but most of my time is spent working with customers, particularly when they want to know how do I use the tools to optimize my code, the Intel software tools to optimize my code. So that's my background, so that's where I sort of come from. I'm definitely a technical person and not a marketing person, although I will behave myself today since we're being on camera. So what we're going to talk about is essential programming techniques for the Xeon Phi. And I've split the agenda into 7 different points, although some of the points I will skip through fairly quickly, and other ones I will spend more time on. The first thing I need to know is of those that are here, and I can't ask the people that are watching on video, but are you programming for sort of x86 for normal PCs at all? Yeah, okay, yeah. So you're programming for x86. But what I'll do is talk first of all about the Xeon Phi. You probably know it's a coprocessor. It's if you get the piece of kit with one in, it looks like a video card, and there's a picture of one there. It runs. You run Linux on it. It's got many cores, and you use normal programming tools. So nothing that's too challenging in that sense. So if you're a programmer, then it's a familiar route to get to using the Xeon Phi. Here's a roadmap of the Xeon Phi. So the cards that are available at the moment are the Knight's Corner, and so that's the ones in yellow. In the future, there'll be a Knight's Landing. One of the big differences is the change in size of the transistors. So we're on 22 nanometer, and we'll go down to 14. And there are some other differences in terms of performance. On the bottom here, this is the regular Xeon processors. So these are the ones that you'd find in your PC or in your server or in your laptop and so on. So, and these names here are the code names that Intel gives for different processors, which helps identify which microarchitecture is being used. Okay, so here's a few notes on the Knight's Landing, which is the next generation. And the three things that you notice, I said already, it's a smaller transistor. The other thing is it'll be available as a standalone processor. At the moment, the Xeon Phi is a coprocessor, so you have to have a card that sits in your PCI Express in a bus. And then the other thing is that there's improvements in performance, and that's really indicated by the last point. So those that are using the Knight's Corner processor already are looking forward to Knight's Landing because there's some further enhancements which will bring the benefits to using the Xeon Phi cards. Here's an internal. I won't spend too much time on this, but a little bit more detail. Maybe I'll come over here. So you can see, well, if it isn't clear already, it's x86 based. So Intel have taken a design of an earlier version of the Intel processor, it's one of the Pentiums, and taken out the main design of that, and then put it into this new design, and it's got 61 cores, and each of those cores have got 4 hardware threads. And those hardware threads are used to service the 61 cores, and I'll talk a bit more about that. And then the other point is that there's some wide SIMD registers. They're 512 bits wide. And again, I'll talk about that in a few more minutes. So what are the key differences between the Xeon Phi and what you might find in your server or PC? Well, the difference is, first of all, there's more cores. As you've seen already, I said there are 61 cores. However, the clock speed is slower. So a coprocessor, it's about 1 gig, the clock speed, whereas the clock speed on your server might be 2.6 gig or even up to just over 3 gig. So you can see there's a between 2.5 and 3 factor of difference in speed. There are the registers, Simdi registers are much wider, and I'll be looking at that in detail in a minute. The coprocessor can handle a greater bandwidth. And then the final thing is that the way that the core is designed of the processor, then the way it deals with the instructions, it does everything in order. And what that means is that in the processor that you've got on your PC or your laptop, then that's what's known as out of order. And so the processor's seeing how early can it execute an instruction or a micro op, and it does things out of order, so it ends up making instructions being executed in parallel, and then it restores the order as it gives the results. So that's on a traditional, that's out of order execution, whereas on the Xeon Phi, then everything is in order. So the instructions are executed exactly in the order that they appear in the code that's being read. Actually, it makes it run slower. So in order is worse. Out of order is all about trying to get performance. In order is not a good design in terms of performance. But that's why there are 4 hardware threads to help service the execution units of the cores. So it's a combination. So the out of order is the reason that we use in order rather than out of order is that in order is less power hungry. So if you take an out of order engine in silicon, there's a lot more power consumed. So power is an important part of the equation. And here's just lost my microphone. Let me put this on. I'll edit this out of the film, I'm sure. Okay, I'm live again. Okay, so here we have there are some details of differences between a regular Xeon processor and the Xeon Phi coprocessor, and you can see some of the details. For instance, clock speed, how many cores, execution style. We won't read through all those, but you can look at those at your leisure when you go home tonight or wherever. Here's the theoretical peak performance. And what we're doing here is, on the top row, this is taking a regular server. So this is actually a server that's got 2 sockets. When you buy a server with a Xeon processor, it's likely to have 2 sockets. So this is the comparison I'm doing. And then at the bottom here, we've got information about the Xeon Phi coprocessor card. And this is using a particular release of the silicon. And on the top, if you take all the different values, so the frequency, how many sockets it's got, the number of cores in each socket, how wide the Simdi registers are, and then how many floating point operations you can do, calculating all the, multiplying those all together, you come up with 666, which I know is an ominous number. Maybe I should put that up or down. And if you do the same with the Xeon Phi, then as you know already, the frequency is lower. It's got 1 socket, 61 cores. The vector width is 16. Floating point ops is 2. And if you do all those together, so we get a value here of 2 teraflops. That's for single floating point. If you're doing double precision, it would be half that. But what you see is that the difference, so this is able to do 3.2 times the number of floating point operations that you could do on a regular Xeon. So that's just showing that there's a performance. You can get better performance by using a Xeon processor. Often when you're working with code, you like to work out, well, what's your speed up been? And over the years, you've probably worked on different projects where you said, yeah, I've worked on this particular piece of code, and I've got a speed up of 100. And it would be possible with the Xeon, if you took a piece of code and did all the optimizations that we recommend, you could say, well, my starting point is x, and I'm now at y, and actually I've got a speed up of 100. But we don't, when we present speed up, we don't do that, and I want to explain that in the next few slides. So when you see a speed up of 2 or 3, which is the expectation we want to set, then I want you to understand its context. So if you take an application, your favorite application that runs for 100 seconds, and if you made it parallel and then you improve the vectorization, let's say you made the speed up, you know, it went, this is the sort of, you got a 4 times speed up because of parallelism and a 2 times speed up because of vectorization. Then you, doing the maths, which is not particularly difficult, then you'd see that with those 2 speed ups, then your application would then run at 12.5 seconds, nothing really difficult. But then if you did some further work on it, so made it ready for running on the Xeon Phi. So the original, your original code was running on just a normal Xeon processor. You've added the parallelism and vectorization, or you've improved it, and you've got those sort of speed ups. So your application on a Xeon Phi, on a regular Xeon, still now runs at 12.5 seconds. You then take that and do some further tweaking of your code and tuning and so on, and then you find that it runs 2 times faster running on a Xeon Phi, then runs at 5 seconds. Now the question is, when someone asks you, how much did you speed up your code to get, you know, how much faster is your Xeon Phi code running compared to, you know, your code running on a regular Xeon, then maybe you'd want to say, certainly to your boss, yeah, we got a 20 times speed up, which is true. Nothing false about that. But actually, the work that you do here benefits the regular code, that other code running on your Xeon, as well as code that's about to run on the Xeon Phi. So you've already done a × 8 speed up of your code by improving parallelism and vectorization. And then here, from this point to here, we've got a 2.5 speed up. And when Intel is quoting speed up figures, what we do is we take the point here and say, we're comparing your optimized code running on a regular Xeon versus running on a Xeon Phi, because we think that's fairer. So when you see comparisons of between 2 and 3 times speed up, it's because part of the work you've done has also impacted on the code if you then run it on a normal PC. Any questions about that? Is that clear? I know it's kind of an obvious point, but I could tell you, you know, we got 20 times speed up, but you know, there are different ways of looking at it, and we've trying to be very fair by comparing it with the absolute tuned performance on Xeon versus tuned performance on Xeon Phi. And these, so here's some benchmarks, and this is running from benchmarks from the Intel Math kernel library. And there you can, the thing I want to highlight is you've got the speed up, so we've got the value, the performance running on a regular Xeon, and then performance running on Xeon Phi. And for all of these, you can see that the speed up is between 2 and 3. And what we're comparing is a piece of code running on a 2-socket, 2.6 gig server, so there's 2 processors on there, versus a Xeon Phi, which is running at 1 gig. So that's the sort of speed up that one would expect. If you read this book, this is a book by a colleague of mine, James Reinders and Jim Jeffers, then in the book he says, vectorize and scale. And that's the 2 things that I'd like you to take away from today. Well, actually, I want you to take away 3 things, but I'm not going to tell you the 3rd thing until the end of this session. I was reading in the Financial Times yesterday, which makes me sound very educated, but it was just free on the train, which is why I was reading it. And in there's an article that said that when people listen in presentations like this, they generally speaking only remember 3 things. So the two things I want you to remember are that programs on a Xeon Phi must be highly parallel and they must be highly vectorized, and we're going to look at those two for the main part of our session now. And then there's a third point I'm going to tell you later on, so you're going to have to just wait. So the three things that you will remember, well, the first two of them is that programs to run on a Xeon Phi must be highly parallel and effectively vectorized. Okay, so, oh, by the way, does anyone recognize that building? You have to live in Reading to understand that building. I often go to Reading because we have an Intel office there, and when I go there, I often pass this building, and one day it dawned on me that the shape of this building was identical to the graph that I've been using for quite a while. So if you look at this diagram and then look here, you'll see the similarity. And what this diagram is showing is that on the bottom here we have the percentage of code that's vectorized, and up the side here we've got the amount of how well parallel the code is. And it's only as you get towards 90–95% vectorization and almost up to fully parallelized, or parallelized, should I say, is that you get to this sweet spot where you're getting a reasonable amount of performance on the Xeon Phi. So the challenge for you as a programmer, if you're going to be using the Xeon Phi, is you have to make sure your vectorization is really pretty good, and likewise that your code is parallel. So might I ask, are many of you writing parallel code at the moment? Yep, so we've got someone writing parallel code. And what about vectorization? Are any of you aware of vectorization, or really don't know what I'm on about? The camera can't see you, they can only see me. So okay, so maybe. So what I'd like to do then is to talk, I planned this, obviously, I knew what the answer was going to be. I'd like to talk about vectorization first and then parallelism. But up front, I want to give you I put a finger in the air. I hope that people that are listening, I mean, you know, it's a guesstimate of how much faster your code might work if you're running on Xeon Phi. And this is assuming that you're comparing it with a two-socket server, moving that code onto a Xeon Phi. And these statements here are all guesstimates. There's nothing, well, they're a little bit scientific in the sense that it's based on some observations, but we couldn't stand up in a court of law and defend the values, because I'm sure you'll find cases where it just isn't so. I mean, they could be greater, they could be less. Okay. So first thing is that if you get a piece of code, if you have code that's both highly parallel and effectively vectorized, then you should expect a speed up of 2.5. So that could be for the whole code, or it could be for a proportion of the code. You've got one bit which you know is well parallel and well vectorized. That bit should speed up by 2.5. If you get a piece of code that's highly parallel, but it's not vectorized, you can expect to speed up about 1.3. I know you can read these slides as well as I can, but the next one is interesting. If you get a code that's not parallel, so it's just a serial piece of code, but you vectorize it and you run it on a Xeon Phi, it will slow down by 1.5. And then the next one, if you have serial code, in other words, it's not parallel, it's not vectorized, then it'll slow down by a factor of 12. So if you want to take your serial code and run it on a Xeon Phi, don't bother. It won't do anything for you. It will go slower by 12. And then the final thing is that bandwidth, the Xeon Phi handles bandwidth much better than the regular Xeon processor. And therefore, if you've got a bandwidth-constrained program, then you'll find that your code will also speed up by a factor of 2.4. So what you could do, if you've got a piece of code and you're trying to say, well, will this really benefit from running on a Xeon Phi, you could try and identify in different parts of your code the characteristics and then apply these, I wouldn't say rules, I said finger in the air, these guesstimates to different parts, and maybe come up with a figure that gives you an idea of how fast your code might run. But as you can see, the fastest that we're saying is that you're not going to you shouldn't expect a faster speed up than 2.5 when compared to running on a 2-socket Xeon system. Okay, so let's talk about vectorization. I asked whether you knew about vectorization. Some of you were shy in saying anything, but I think that you'll find this quite relevant for what you're doing now. So what's vector processing? So here we have what we call a scalar processing. Don't worry about the instructions. It could be any instruction set architecture. The principle's the same. So here we have, you're just doing an operation, R1 plus R2 equals R3. We call that a scalar calculation. It's possible to do lots of calculations at the same time in the same instructions. So we have lots of vectors. So V1 contains a number of vectors. We call this the vector length. Add them together and you get another value. In vectorization, what we're doing is this kind of calculation. You've got one instruction that will operate on multiple elements of your data. So, for those of you that, I'm trying to look around the room, so I don't think any of you are in this category I'm about to ask. Do you ever remember when you first bought your first PC as to whether you were going to have an x87 or an 8087 processor on it to do the floating point calculations, or whether you got the cheaper version and had to use an emulation library? You're all looking pretty, well, no, two people are sort of, nodding at me. What happened was, certainly when the first computer I got, I couldn't afford the coprocessor that did this floating point calculations. And it's part of the history of how the processor was developed. So before 1999, then there was the addition of the coprocessor for doing floating point, and it was a separate processor, which eventually those floating point calculations are the part of the electronics that did floating point calculation was incorporated into the processor itself. And then from there, over the years, there have been a number of enhancements to how different types of calculations have been done. And with vectorization, as I've already said in the previous slide, that the idea is that we have instructions that can do more than one calculation at the same time. They're working on multiple sets of data. And this diagram here shows the different enhancements to the SIMD, single instruction multiple data type instructions that are supported by the processor. So right at this end, we have the AVX 512. We've lost the end of the slide for some reason here. And back at this end, SSE was brought in 1999. So SSE2 is, I think, where most people think of in terms of the starting point for doing SIMD programming. And you can see over the years that there have been more instructions, but also the registers that they use have got wider and wider and wider. So here we've got 64 and 128-bit vector registers, but when we come to the registers that are on the Xeon Phi, then they're 512 bits wide. One of the ways that you can get your code vectorized is to use a compiler. And this is the example of how the Intel compiler can take code and vectorize it. It's actually showing a particular part of something called Silk Plus, which has got some expressions for expressing code that can be vectorized. We'll look at an example of that later. But what the compiler will do is vectorize the code and translate it into whatever target you're aiming for. So you're maybe asking, how can you get your code to be vectorized? Well, you could write in assembler. I might ask, how many of you writing in assembler? No, not at all. Or you could use various intrinsics, or you can use a library class that's available. And at the top end, you've got ready usable libraries that have already been optimized by the developers of those libraries. So there's different levels of control that you can have. If you really want to have the fine, detailed control, you'd be down here, but you've got to be knowledgeable about the the architecture itself. Most people are working more at the sort of automatic vectorization or some of what I call the explicit versions of being able to of adding vectorization to your code. So let me give you an example of array notation. So let me just go back one slide, sorry. So if you see, I've got silk plus array notation as a third one. So the next few slides are giving some examples. I'm going to gloss over some of these because I want to come on to a case study in a while. So here's an example of silk plus array notation. It's an extension to the C language. It's supported by the Intel compiler. It's already there's a version of GCC that support it, and it may be that at some point in the future it will become part of the one of the standards. It's not there yet, but there are discussions. So what the array notation does is it allows you to write code to manipulate arrays. So rather than having to do everything in for loops or specific indexes into your loops or doing pointers and so on, then you can use this new syntax to manipulate whole arrays at a time. And the reason for doing, or the benefit of doing it is that the compiler will then vectorize that code. So let's give you an example. So let's take a loop here. So here we have a loop that's, well, you'll recognize it just going around, and we're doing something with each element of the array as the loop index is increased. On this side, there's no loop. So what we have here is each of the arrays, and we've got some syntax here which includes a colon in the middle. I'll give a bit more detail about this in a moment. And what this does is, in this case, every element of B is added to every element of A, and the result is put in A. And two things that we have from this is, one is that the compiler is able to vectorize this, and then secondly, let's say you don't have to have the loop, so it's an easier way. It looks when you start writing the code, your code in most cases will look easier than if you've got for instance nested loops and so on. So let me give you an example of that operator. So when you use the colon inside the square brackets for an array, it's a regular array, nothing unusual about it. Then this accesses all of the array, so we're accessing all 4 elements. The full syntax is that you can express the lower bound, how long the element is, and then there's a stride, so you can say every second one. This is an example of accessing 4 to 7. The next few slides, there are more examples, and I'm not going to go in detail. You can look at those when you have time. So there's how to do columns. That's how to access a cube or a block. Here's one where you're wanting to have a stride in between. This is an example of just showing the equivalent longhand of doing a calculation. And then along with the array notation, there are a number of functions that are available. Here's doing a shift and rotate. Here's one for doing various reduction algorithms. And then what you also can do is that for an array, you can apply a function to each element of the array, and that's called function mapping. Okay, so that was the array notation, and I'm going on at a speed because I want to talk at a higher level, really, about the consequence of vectorization. But here's another way of getting code to be vectorized. You probably recognize this piece of code here from the earlier slide, and the compiler couldn't vectorize it because there are things that it didn't know. And the things are, it didn't know whether any of the elements would overlap each other. That's the main thing it couldn't work out. And by putting a pragma SIMD or using array notation, then that gives sufficient information or instruction to the compiler to say, by putting the pragma SIMD in, you're saying two things. You're saying that these are not going to use overlapping areas, and also actually that you know that x is always going to be a negative number there. So it's effectively increasing this value. The Simdi Directive, you can add some clauses to it. If you're anyone familiar with OpenMP programming? Yeah, some of you are. So there's some similar clauses like OpenMP in terms of talking about how variables are accessed within the Simdi directive. And then the third way that you can add vectorization into your code with array notation is to use vector elements or Simdi functions. And what happens here is that you have a piece of code. So we have a loop here. We've got a function up here that's got the special attribute vector and so on. You can see it there in blue. When the compiler sees this pragma here, and then we come to this function, it recognizes that this function is capable of being vectorized, or it has been vectorized. And so it will apply a vectorization to the elements that have been sequentially accessed in this loop. So rather than calling the function, it will use a Simdi instruction for each one of those separate calculations that are being done there.
If I have a Fortran 90 or Fortran 95 program, do I still need to use this?
Yeah, the directives are slightly different for Fortran, but it's available in Fortran as well as in C, yeah. And there are some various, again, clauses to do with the vector functions, but we won't go into the detail of those now. So, well, you're thinking, well, I'm not sure whether my code is ever vectorized or not. I'm not sure of its significance. I've never really tried to put vectorization in my own code. Or maybe you have. But there comes a point when you have to say, well, is my code vectorized? And if you're using the Intel compiler, then we provide a way of finding out if your code is vectorized. You do an extra option, and you get a report that gives you information about how your code is vectorized. And there's a whole list of anything from not having any information to having just too much information almost. Here's an example of one of the most verbose outputs from the compiler. And what the Vec Report 7, it gives information that can be processed with some additional scripts that we provide. And so it will give you a detailed report on every line of code as to how it was vectorized. So that's one way, and there's a link down here if you want to find out more about that. But the other way is that you could show how good you are as looking at assembler by looking at the instructions. So here's an example of an instruction. Now, just because a piece of code looks like it's vectorized, it might not be. Just because they're using the special registers that are used in SSE, for instance, or in AVX, it doesn't mean to say that the instructions are being used are doing 4 calculations at once, for example. And so here's a case in point. So we have here an add SS. So this is a scalar single add with floating point. And when that instruction is used, it's only really adding one value to another value and doing a result. It's only when the packed equivalent is used, so there's a letter P here, so the packed single floating point add is used, that all 4 calculations are done in the one instruction. So one way that you can check whether your code is vectorized, or indeed anybody's code, is to do either disassembler or generate an assembler source file when you're building, and look at the instructions and try and see whether the existence of packed instructions. And I know it looks kind of simple, but on the whole, it is. Sometimes the P isn't there, sometimes it's at the beginning of the instruction. But there's a way that you can check whether your code is vectorized. So here's an example of some generated code. So that loop there, if it's vectorized, it can be we've got 3 different versions. We've got Mike, AVX, and SSE2. And the thing that you will note is that it's a loop. It's going around 1,000 times. And what we're doing is we're doing a calculation. In the assembler, what the code does is it does the same sort of calculations, and each time it goes around the loop, there's a test at the end, it increments the counter that's controlling the loop. So here, in the SSE example, it increments the loop counter by 2. If you look at AVX, it increments the loop counter by 4. We're comparing with 1,000 in each case at the end to see whether to finish the loop and carry on. And in the case of the mic, it increments the loop counter by 8. And the reason that it does that is that for the different architectures, the Simdi registers are a different width. So in SSE2, it's 128 bits wide. In AVX, it's 256. In mic, it's 512. And so with the packed instructions, you can do twice as many instructions here as you can there with one instruction, or twice as many calculations, and likewise with mic compared to AVX. So that's why the loop count is done, is incremented at a different value in each case. Okay. A while ago, I worked with AWE. Does anyone know who AWE are? Atomic Weapons Establishment. So what I'm saying now is public. There's nothing, you're not all sworn to secrecy. They have a website which publicizes the work that they do, and so on. And so a while ago, AWE approached us and said, we'd like to do some preliminary work on some of our public codes to see how they'd run on Xeon Phi. And the next few slides are showing some of their results or their experience that they had. This is the application. It's called Cloverleaf. It's sort of a mini app. You can download, if you Google for Cloverleaf, you can download the code and try using the code yourself. But what they found out was that taking their original code, it having been optimized, and then running it on Xeon Phi, they were able to get a speed up of 1.7, so nearly 1.8. The code that they wrote was written in MPI, and then they had OpenMP as the nested, so it was a hybrid solution. So it was MPI and OpenMP. And what's interesting in what they're doing is how much vectorization had an impact on the code that they did. So here is an example. This is the improvement that they got by introducing vectorization. And the slide sums it up, is that the code ran 80% better when it was vectorized, okay? So this is on the Xeon Phi program, on CPU. The same code, when it ran on a regular CPU, then it was between 25 and 30% better, depending on whether they're built for SSE 4.2 or for AVX. Here's a graph of showing how their speed up compared with, so as they increase the number of cores and threads, then this is how the two platforms performed. So this is the runtime speed, so obviously lower is better. And then here you can see that on the Xeon, on the workstation itself, then there came a point when the maximum sort of performance they got was about here. They ran it with a maximum number of cores available on the particular machine they were using. On the Xeon Phi, as they increased the number of cores beyond 60, then there wasn't any real improvement. And you know the reason for that, because you know that there are 61 cores on the Xeon Phi. So that's why, in their case, there wasn't any appreciable improvement beyond there. And this is a summary. This is quoting directly from AWE, as you can see, it's an AWE slide. And depending on how you do the calculation, well, they've got here that they've got 3.14 speed up. One of the reasons that some people want to use Xeon Phi is because of the amount of power for the performance. So they said that when they ran the code running 240 tasks, then it was 230 watts on a Xeon Phi. If they ran it on a normal Xeon, it was 150 watts. But if you then did the calculation so that you matched up the performance, how much calculations you'd achieved, then that was really the equivalent of 450 watts. So that if you managed to achieve the same calculations on the Xeon Phi that you did on the regular processor, if you were able to, then you would have done effectively 450 watts. So it's more power effective. I don't think that came out very well, but what I'm trying to say is that it's more power effective to do the calculation. So watts per flop, for instance, is better on the Xeon Phi than it is on the regular Xeon. And that's one of the reasons why some developers are looking at the power, not just performance that they're interested in. Okay, that's something about vectorization. So just to sum up the vectorization means that your code can take advantage of these extra wide SIMD registers that, along with the compiler, will get you good performance. But the vectorization on its own is of no use unless you make your code parallel. Some of you are already writing parallel code. On the Xeon Phi, as I said earlier, there are 4 hardware threads that work to make the parallelism and make the cores work at the best. So 61 cores, and underneath it there are 4 hardware threads. When you're writing your threaded code, then the recommendation is that you experiment with using between 3 and 4 threads per core to see what your best performance is. So the question is how many threads should one use? And again, quoting from this book here, says an application must scale well past 100 threads to qualify as highly parallel. So if you've got a piece of code that you can't justifiably or easily get to run with over 100 threads, then it's not a suitable piece of code for Xeon Phi. So languages to help you to write your code parallel. Well, you can do native threading. I've mentioned there's MPI, there's OpenMP, there's threading building blocks, which is a C++ template library. There's Intel Silk Plus, which I'll talk about briefly. If you're in Fortran, you can use Fortran coarrays. So let's have a look at a couple of these. So first thing is OpenMP. How many of you are familiar with OpenMP as a programming? Sort of. Okay, the next few slides just skip through a few things just to give you an idea of introducing parallelism. So OpenMP works by, you can, as a programmer, can insert pragmas into your code, which, so you get a piece of code, you say, I'm going to work on making this bit, particular loop, for instance, parallel. So you put a pragma around the loop, and that bit will become parallel. It uses a sort of forking into threads and then joining at the end. So this diagram here gives the idea that there's a master thread running through all your program, and you'll choose parts of your code to make parallel. So it's not the case of saying, let's make it all parallel, but rather bits of the code that will be made parallel. And usually, but not always, then it's loop-oriented parallelism is what people implement. Here's an example of an OpenMP loop. So it looks like a regular C++ loop with the extra parts in the pragma. So what that does is that Once the parallel part, at that point when the runtime sees that statement, then there's a pool of threads made available, created. And those threads are then given the work of this loop is shared between the different threads. So it's a standard that's been around for quite a number of years. But you can use both Fortran and C to do OpenMP, and it's a way of easily incrementally adding parallelism to your code. Another way of adding parallelism is Silk Plus. I've already talked about array notation. That's to get the vectorization. But Silk Plus has also got part for adding parallelism. So we've got 3 keywords. We've got Silk Spawn and Silk Sync and then Silk 4. And then there are various objects to help, sharing data between different workers or threads. So they're called reducers or hyperobjects. I'll do an example of that now. So here's a piece of code that what we have here is it's a matrix transpose, and we've got a double nested for loop. They look like normal pieces of code. They look like normal C loops, except for the name of the for loop has got the silk in front of it. And what that will do is that the loops will be shared amongst the workers, which is really equates to threads. And what you're doing as a programmer in Silk Plus is expressing an intent. You're saying, I want this to be parallel, but it's up to the runtime whether actually it is made parallel, and it depends on the resources available. So the way Silk Plus works is that it will see if there are spare workers available, and if so, it will use a concept of task stealing to say, right, that worker's not doing anything at the moment, let's get these loops or this part of the work and give it to that task. But what it doesn't do is, if you could put Silk 4 onto a loop, and if there are no workers available, it will still run serially. The second example is using the Silk Spawn and Silk Sync. Again, this is about giving permission to the runtime. So what Silk Spawn does, it says, you can run the next piece of code in parallel with this piece of code. It's giving permission to the runtime. It's not creating new threads, even though the word spawn's there. It's saying the piece of code on this line and the code that continues underneath can be run in parallel. So, and then until you come to the sync point here. So you find here that this is a recursive call of Fibonacci, and the runtime will decide if there are workers available to run some of those iterations in parallel. Okay, from a programming point of view, if used for using Silk Plus, then you just have to include a header, use the keywords. You can use various APIs. They're all involved in setting the number of workers. So very limited control that you have from the API. It's just about either getting information about how many threads are available, workers, or setting them. And then likewise an environment variable to do the same thing. So that was Silk Plus. So what have we done so far? We looked at making code parallel. You can use OpenMP, or you can use Silk Plus. And the other method we're suggesting is that you could use threading building blocks. Threading building blocks is a C++ template library. So if you enjoy C++, if you enjoy templates and all that comes with it, and some people love that, there are some people who hate it. But if you really feel comfortable with threading building blocks, then with C++, then threading building blocks might be the right way for you to add code. It's available in source code as well under GPL, and it's become very popular in many industries because the source code is available. A number of people have ported threading building blocks to different OSs and to different architectures. So here's some of the things that the threading building blocks contains. There are a number of algorithms. You can recognize some of those by reading what the names are. There's a scheduler that takes care of what's happening underneath. And again, threading building blocks like Silk Plus works on the concept of task stealing. So tasks that are busy have work taken away from them and given to tasks that are doing nothing. So it's a sort of balancing out of the work. There are various synchronization primitives that you can use. Those are used when you have shared or global variables, for instance, and you might want to use you need to make sure that those are only accessed by one thread or at a time, and so that's where those primitives would be used for. And then there are various containers, somewhat similar to the STL containers. Again, if you look at the names, you'll see some similarities. I mentioned earlier that with AWE, they were using MPI and OpenMP at the same time. So here's just a slide of an example of using MPI to get the parallelism across the different cores, and then within the core itself, using OpenMP. So MPI is a message passing interface, yes. I'm trying to think of a different word. If you're come from a sort of a university background or in high-performance computing, you'll be very familiar with MPI. But so what happens is that naturally that you can use MPI code to get your code running onto different cores, and then once that code is running on a core, then you can use the OpenMP within that code to then take advantage of the hardware threads available on that core. The next 3 slides show you examples of making code parallel using Silk Plus, threading building blocks, and OpenMP. I won't talk in huge detail, but I will just quickly point to them. So here's a loop. In all 3 cases, you've got C loops. So all my examples in C, but there are the OpenMP you can also do in Fortran as well. And you can see in the 2 more straightforward to understand, I think, are the Silk Plus. It's just a different word for the 4. In OpenMP, it's just putting a pragma. This one is slightly more complicated. It's still a 4, but there are some values that need to be passed in. And what we're using here is a feature of the C11 standard. So we've got Lambda functions. They're anonymous functions where you can declare the body of a function in place without it having a name. And it happens to make life easier in terms of working with some C++ codes to use Lambda functions. Here's an example of sections. So sections are where you'd have 3 different pieces of code and you want them all to run in parallel, but they're not in a loop. So what we have is we've got, again, the 3 different Silk, TBB, and OpenMP. And you can clearly identify the 3 different functions that are going to work in parallel. OK, so what I want to do is talk about on to the next topic, which is bandwidth. I'd already said that you must have your code which is highly scalable and effectively vectorized to make it run well on Xeon Phi. However, you can get code which isn't so well, for instance, highly vectorized, but if it's bandwidth constrained, you still might get a performance benefit by running on Xeon Phi. And here's I gave you this slide earlier on, where I glossed over one result. So this was the results from running some benchmarks with a math kernel library. On this end, here is a streaming program, and the performance is in how much data is being transferred. So it's gigabytes per second. And what we find here is that running this streaming benchmark on the Xeon Phi, we get a speed up of up to 2.2. So it might be in your code that, if you know it's bandwidth constrained, you may get a benefit of running on Xeon Phi, even though for instance, it might not be as well vectorized as it should be. Programming models. When you write your code for Xeon Phi, there are a number of different ways of writing your code. On the one hand, you could have, so what we've got here is we've got a range of different ways of writing your code. On the top here, we've got the what is equivalent of your normal PC or Xeon core. On the bottom here, we've got the bit of program that would run on the Xeon Phi. Okay, so on the one hand, you could simply have a program that just runs on the main PC and doesn't run on the Xeon Phi. Well, that is a programming model, but it doesn't take advantage of the Xeon Phi. Right at the other end, you could have a program that just runs on the Xeon Phi, but doesn't do anything on the PC itself. And in between, there are a number of different models. So here's an example where you have a piece of code, let's say you've got main and foo and so on, where this code runs both on here, but part of it also runs on the Xeon Phi. That's one model. The other model would be where you're running, well, you're treating your Xeon Phi as if it was just another node of your computing. So everything that's running on your normal processor also runs on the Xeon Phi. And then here, it's actually the reverse, where you're saying the code starts off by running on the Xeon Phi, and then it sends part of its code up to the Xeon. This model's not supported at the moment. So that's the variation of what you can have. So from running just on your workstation and not using the coprocessor at all, to running code which runs actually on the coprocessor itself. Any questions on that at all? No. So here's an example of code which, so it's calculating pi, and what we're showing here is a piece of code, and we're going to get part of the code to run on the Xeon Phi. So what we do, first of all, is add OpenMP to make it parallel. So rather than running in just one loop, well, it still runs in the loop, but it's then shared amongst all the available hardware threads. And having done that, we put a second pragma, and we say offload target mic. And what the code will do is that as the program runs on the main workstation, we come down to this point, and we have this pragma offload target. Then this code will run on the Xeon mic rather than on the workstation itself. So this is quite a simple example of doing what's called offloading. So let me just go back to the previous slide a second. So here we've got an example here where everything's running on the Xeon Phi. That wasn't the case in the code that we just did. So what we were doing was we were just taking parts of the code and offloading it. So here we are. You can see at the top where it says offload here. So what we've done is we've taken some of the code. In our case, we used a pragma to offload part of the code to run on the Xeon Phi. So let me go back to that slide again. Okay. What you can do, and I'll go back to my previous slide again, you could have all your code running on the Xeon Phi by just treating it as a machine that's got Linux on it, and you can SSH into it, and you can just build your code ready for running straight onto onto the coprocessor. And you even have a terminal, and it just looks like you were just remotely logged into a Linux box. Right, here's another case study. I've written this as a bank near you. I don't know you. I don't. I've worked a while ago with a bank. I can't say which bank, but possibly we own most of the bank between us. If you can work that one out. And what they were interested in doing was they wanted to run their codes on Xeon Phi. And they had 3 reasons for being interested in that. Well, they have a particular, this is only part of the applications that they had, but in their code they had a product that took in product and market data, various other controls, and they were trying to work out the value of investments, for the next 50 years. So it's an important part of helping the investors to make decisions. That work, part of it, particularly down at the valuation phase, that could typically take 50% of the time. So if we could make that parallel, then hopefully, in its Monte Carlo, that's a good piece of code for making parallel. Get that running on Xeon Phi to reduce the time. And the reasons that they wanted to reduce the time were for 3 reasons. The first one is they got to the point was when they did their overnight runs, so the bank would, there would be lots of investment decisions and also models that need to be run overnight. They got to the point was where it was taking more than half the night to run the model. And if it failed, there wasn't time to rerun the model. And therefore, when it failed, you had to use the day before's result. So the next day, the investment bankers had to use data that was 2 days old. Well, most of the time, that probably isn't the problem, but occasionally, it could really hit them. So they would find they're making decisions on data that's 2 days old, and it could be a disaster. The second reason was that the cost of renting data centers. So the particular data centers they were using weren't their own. They were, these are the things that do all the number crunching, a huge number of servers. They rented space from elsewhere. That space is rented to them on how much floor space they took. And they had this idea that if they had servers that had coprocessor cards in them, they'd physically take up less space and somehow reduce their total rent that they had to pay on the data centers. And then the third thing was the power consumption. They realized that the Xeon Phi, that its flops per watt was better. There's a better performance per watt than a regular Xeon, so it was another way of reducing costs. So those were the things they were interested in. So I spent probably about 5 or 6 months working with one of the engineers. They took the code out from their original very large collection of investment tools that they had. We made a standalone code which had some of the key analysis and code that did the calculations into a separate sort of harness. And the first thing we found out was that the code wouldn't vectorize very well. So if you remember the first part that we said that code had to be well vectorized, and the reason that the code wouldn't vectorize is that for code to vectorize well, then for instance, if you're going a loop and doing calculations on an array, you must go sequentially through the array for it to be vectorized. You can't vectorize non-sequential access to memory. Well, you can, but it's very inefficient. Okay, there are occasions when you do that, but it's just not efficient. So you need to vectorize. You need to have sequential access to code. So the first thing we had to do was to take the code and re-engineer nearly all of their data layouts. So that they had what is called an array of structures, which is a bad model. So they had an array, and inside they had pointing to different objects that they were instantiated. And inside those there were data. What they needed was a structure of arrays. Okay, so and so we reversed the way that they did things. And what that really means is collecting, like types of data together into structures, so that on this particular kind of variable, you can quickly go through all the variables and it's sequential, rather than going through an array that has a class, and each class has got separate data elements in a sort of disjoint manner. So the first thing you had to do was to change their array of structures to structure of arrays. That was the biggest change they had to make. I didn't do the work, someone else did it. It took them probably 2 or 3 weeks of hard work, and that made the biggest difference. Now, what I can't do is show you more of their results, but I can show you some slides of a similar piece of code. And that is a Black Skulls sample code. And this slide shows the effect of running a Black-Scholes application, which again, he was doing some very similar types of calculations to what the bank that we were working with was doing. And so what we have here are 3 slides that at the top, it shows the results of running code on the Xeon Phi. So the left is the regular Xeon, and the right is the Xeon Phi. Okay, and bigger is better. So you can see that the Black-Scholes running on the Xeon Phi ran better than on the Xeon. But if you were to just vectorize the code, so you ran it on a PC and it ran here, that's the performance. If you ran that vectorized code on the Xeon Phi, but it wasn't parallel, it would run much worse. Remember, bigger is better for this graph. If you got the code and made it parallel, then running it on the Xeon Phi parallel, again, the performance was worse than running it on the PC. It's only when you had both parallelism and vectorization together that we got the performance. Now, you should know that from what I've said already during this afternoon. Here's a summary of some of the timings that they did. What this is showing is that how they incrementally added different kinds of optimization to, not to the bank I was working with. This is a different Black-Scholes example, and they were able to get the calculations working better as they added vectorization and parallelism. And the summary of from the Black-Scholes example is that they took a Black-Scholes example, and it was initially using just under 2,000 cycles to do its calculations, running on the Xeon Phi. By the time they'd done the vectorization, the parallelism, then they got it down to 200. Now they've done this thing that I said we don't do. They said, oh, it's speed up by a factor of 10. But you'd find that the optimized code that's running on the Xeon Phi will also run better on their original machines as well. Okay, the next points are things I want to alert you to, is that when you're programming for Xeon Phi, as I've said from the beginning, you have to be vectorized and parallelized. If you've got bandwidth constraint, then you probably benefit from running on Xeon Phi. You can do different programming models. Now we're getting down to some messy low-level detail, which some of you are probably very comfortable with low-level detail, others of you not. But you've got to consider what's called affinity, alignment, and prefetching, and then we'll consider low-level programming for a moment as well. So what's thread affinity? If you have a processor and it's got lots of cores, how your threads are put onto the different cores, you can control the way it's done. And maybe I best do it with a diagram before I go into any slides. So let's say you've got a machine with 2 cores, and each of those cores, well, I'll put 3. I don't know what kind of processor I've got here, but it's got. So it will. So we've got two CPUs, and each of them will support 3 hardware threads. And so you've got a program, and if you make your program parallel, then when it's running parallel, let's say you've got a program that just runs, I don't know, it's got 6 threads that run at the same time. I mean, you could have it allocated like that, 4, 5, 6. Or it could be that you decide that you want the threads are done 1, 2, 3, 4, 5, 6, or some other way of doing it. So what affinities is about is how are the threads tied to the particular core, to the particular processor, rather, that's being used. And those different values are for use with OpenMPs. So you've got physical, compact, scatter, and balanced. On the next slide, I just want to show you the difference between 2 of them. So this is the compact and scatter. So on compact, then the OpenMP runtime will allocate each of the threads on each physical core in turn. So first of all, it'll fill up all the threads on the first core and then on the second core. Whereas if you do it scatter, then what we'll do here is that it will go across. So first it will put a thread here, then a thread here, then a thread there, and so on. So well, you're probably asking, well, why is this important? It becomes important, first of all, if you don't use all the cores in the CPU, then it becomes more relevant as to what kind of affinity. So, for instance, if you're not using all 61 cores, if you're only using 20 of the cores, it will become important of what kind of affinity. And it also will determine, if you've got a code that's also bandwidth constrained, you want to use the buffers to write to memory. Those are shared across the different CPUs, so you want to spread across as many CPUs as possible, for instance. So there are different reasons that you would want to control how the threads are put onto the different cores. You might have written a piece of code where the first 4 threads are all working on the same data. So ideally, you'd want those to be in the same cache for this. They want to be on the same processor rather than on a different processor. Okay. The detail we can't go into. I mean, normally we'd sort of spend probably half an hour talking about this. So that's something. So you have to put in your mind affinity is important, particularly the preset ones that let me just go back a slide. These 4 here. If you starting to programming in OpenMP, one of the first things you ought to do is to experiment with those different affinity attributes, because it will make a difference on your codes. The other thing that you need to watch out for is alignment. Your access to arrays not only need to be sequential in terms of vectorization, but they also, the arrays themselves should be aligned at least to the cache lines. So in order for most effective use. So there are different ways of aligning data. You can, first of all, create aligned data by using this malloc instructions. You can then declare variables that will be aligned. And you can also inform the compiler. You can say, well, this particular array that I'm working on, this vector I'm working on, is aligned. Because the compiler won't always know. Because if you've written a piece of code where it's just pointers being passed in, and that information about that is in a separate compilation unit, it may not know. So you can tell the compiler. And there are a couple of ways of doing that. And then the other low-level thing that you can do is to prefetch. So if you are accessing data, then what the processor is trying to do all the time is make sure that you're not having to read from external memory, but the data is already in local cache. For the Xeon processor, that's done automatically. There's hardware prefetching and what's known as software prefetching. In the Xeon Phi, we rely on software prefetching. The compiler will insert prefetching instructions. You can insert more of them yourself, and you can use the compiler, if you're using the Intel compiler, to get a report about how much prefetching has been put in. Here's an example of doing it manually. You can use intrinsics or pragmas to force prefetching of data. Okay, right. And then finally, I'm going to point to this next section. I don't expect that to have any real discussion about this. Just to say that the way that the runtime works for offloading code is that there's a high-level offloading. So for instance, we've got an example here of using a decal spec for offloading. So you've got a piece of code, and some of the code is going to be the code running on your main machine, it's going to be offloaded onto the Xeon Phi. That top layer of offloading, which is generated from sort of C code, underneath it there's an intermediate runtime layer, and that runtime layer sits on top of a low-level CIF layer. It's possible, and there are some people developing, for instance, code for fast trading, who write the offloading code down at this level. So this API is available for you, but you've got more direct control as to the offloading, and there are sets of APIs. I don't have, well, I've got the block diagram of the APIs, and you can see here, so this is the host side, this is the Xeon Phi. At the bottom level, then the physical layer is used as the PCI Express. And this is showing the different stacks of how the host and the target communicate. Normally, you're relying on the top level. As I say, you can, down at this lower level, you can use the CIF drivers to communicate between the two. And if you're doing something that requires a very, you want to have much more immediate control over what's happening, then you could consider using the CIF interface to do your offloading. Okay, this I'm going to finish with. You remember that there were 2 points. Do you remember the 2 points? As I said at the beginning, that according to the Financial Times, you're only going to remember 3 points from this. Well, I'll tell you the points you're going to remember. The first one is that your code must be highly parallel. The second thing, it must be effectively vectorized. Will you get any idea what my third point is? Sorry? Bandwidth. It could be that, but it's not going to be that. That would be a possibility, but it's not going to be. Well, my third point is that whatever you do to your code to make it run on a Xeon Phi will benefit your existing code. And what I mean by that is you do the work on your code to make it more parallel, more vectorized, so yeah, it runs on Xeon Phi. You run that same code on the original machine that hasn't got Xeon Phi, and it runs faster as well. So whatever optimization work that you do, it benefits your existing code. And actually, that highlights the fact that not many of us are that good at optimizing our code. I mean, in a sense, if our code was highly parallel and effectively vectorized already, we shouldn't be going through this. But the truth is that most people are quite happy to quickly do their optimization work. As we work on it to get code ready for Xeon Phi, it will be, even if you don't ever run the code on a Xeon Phi, you decide, no, it's not the right thing for this particular application, you'll find that your code will run faster on the existing platform as well.